Hello all of you. So in the last lecture we have been discussing the canonical ensemble and basically the meaning of the temperature or the variable beta that we defined in the last class. So in today's lecture we will take the canonical ensemble a bit further and talk about how can we write Helmholtz free energy for the canonical ensemble as a function of the partition function, and then I will discuss briefly how to compute the averages and fluctuations using the canonical ensemble. So, essentially where we were so far is that we have defined a partition function for the ensemble, and now I am talking about the systems that are same in the ensemble, not really the close contact that we assumed earlier in the last class. In this case, let us say again going back to our earlier treatment, we have some A systems each having some number, some volume and temperature, and they are forming an ensemble. So, of course, they are not in any close contact except with the bath, and the bath is infinite and that maintains the temperature of the system. But the energy of the systems can be different, which are characterized by Ej, that refers to different energy levels that are possible in the system. So, now I can define a variable ln of q or ln of summation over j e to the power minus beta j, and it turns out this particular function has very interesting significance and it relates to the idea of Helmholtz free energy. So, if I start with this function, what we can notice is this function is a function of the beta variables and the Ej variables, and therefore, I can represent the total change in this function df as the change in the beta variable represented by a partial derivative. So, change because of a change in beta variable dou f by dou beta that has to be evaluated at constant Ej d beta plus a change in the Ej variable that has to be at constant beta and constant value of all the other energy levels apart from Ej multiplied with dEj, and since we can do this for all the j value, there has to be a summation over all the j value. So, now if I find the dou f by dou beta, what we notice is that the dou f by dou beta is something like 1 by q dou q by dou beta, that is summation over E minus beta Ej, and you have summation of E minus beta Ej multiplied with minus Ej in the numerator, because we take a derivative of minus beta Ej with respect to beta, and that is equal to minus E bar. So, just like we can do that, we can also find the dou f by dou Ej, and then we notice that that quantity is 1 by q dou q by dou Ej. Again you will have summation over E minus beta Ej in the denominator, but in the numerator you have e to the power minus beta Ej, and now the derivative of minus beta Ej with respect to Ej, and that is minus beta, and this summation will not appear because only for that particular Ej value in the summation you will have minus beta. For all the other energy values you will not have a derivative. Let us say if we are doing for E naught, E1, E2 and so on, if I do with respect to E naught, only the term containing E naught will give me a derivative, everything else will give me 0. So, this thing is then equal to minus beta E minus beta E j by summation of E minus beta E j, and this quantity we already have obtained, and that is the probability of the states of energy E j. So, therefore, if I now put whatever we have got here and earlier in the previous expression, what we find is dF is equal to minus E bar d beta minus beta p j d E j summation over all j. So, you can notice that I am replacing this quantity by minus beta p j and this quantity with minus E bar. So, now I can define a quantity f plus beta E bar, and for this quantity the total derivative is equal to dF plus beta dE bar plus E bar d beta. If I now put the expression of dF from here, what this gives me essentially is beta dE bar minus beta summation of Pj dEj, which we can write as beta dE bar minus summation over Pj dEj. Now, let us look at the second term in the expression and think that we are doing a reversible process in this canonical system. We start with some NVT and now we are changing the volume by a small amount, and due to the change in volume the energy changes by dEj, right. So, then for a reversible change, you may recall that when we discussed like what the heat and work is doing to the system, I told you that when I am adding heat you get an extra quanta of energy and that quanta can be distributed in all the states. But when I do work, I am essentially changing the energy level spacing. So, what will happen then is if you had some systems Aj which had energy Ej, after doing this kind of a work, the energy of those particular states will change from Ej to Ej plus dEj. The key point is that the occupation level of states are not changing, only the energy level of a particular state is changing when I am doing the work. When I am adding heat, then of course, you will have more distribution of quanta of energy, because we thought that it will be addition of an extra quanta of energy. In some sense, work is also an addition of quanta, but what the work is doing, it is changing the energy levels to different values. So, then let us say if you have certain number of states here, certain number of states are still going to be there, but those states are going to have higher energy than the previous configuration before the work was done. So, if we go with this particular idea, then the average work done can be thought of as Aj multiplied with dAj. So, all the Aj systems we are doing Aj multiplied with dEj work, and this has to be averaged over all the systems in the ensemble, and of course, this has to be summed over all the possible energy levels. So, this essentially gives me summation of Aj by A dEj and Aj by A essentially is the probability of states Pj Dej, and that essentially means that we can think of the Pj Dej term as some sort of work done on the system. So, now if I invoke the first law of thermodynamics, then you have dE is dQ plus dW. The energy, the change in internal energy is equal to the heat added plus the work done. So, for a reversible process, what we have here is this is equal to beta and change in the heat, because we are doing energy minus work, and that must be equal to the heat added, and we already have assumed that the process is reversible. So, that is beta delta Q reversible. I have put a delta here just to indicate that this is a path dependent thing, unlike energy that is a state function. In fact, Q is also path dependent. So, now if I use that argument of Clausius, what Clausius has said is that my change in the entropy ds is equal to my heat added for a reversible process divided by temperature. So, using the definition of beta I found in the last class, you have beta is equal to 1 by kBT, and I can replace delta Q reversible by T ds. So, this thing therefore is ds by kB. So, therefore, I can write d of f plus beta E bar is equal to ds by kB, or in other words I can write S as kB multiplied with f plus beta E bar, and that is, if I put back the expression of f, it is kB ln Q, and using the expression of beta it is E bar by T. So, this we can also rearrange, and we can see we can write E bar minus Ts is equal to minus kBT ln Q, and E bar minus Ts is the definition of my Helmholtz free energy. And therefore, you have Helmholtz free energy as a function of the partition function in the canonical ensemble. That should not be unusual, because we have earlier established that whenever the control variables are the number of molecules, the volume and temperature, we should be using the Helmholtz free energy. If in this case the control variables were the number of molecules, pressure and temperature, we would have gotten the Gibbs free energy, but the fact that it is coming as a simple function of the partition function tells me that if I know Q, that is equivalent of knowing the Helmholtz free energy, and if I know the Helmholtz free energy, I can do thermodynamics and get all the properties, and that is indeed true. That, as I said in the last class as well, that Q works as both a normalizing function and a generating function. So, knowledge of partition function is like giving you the knowledge of the entire thermodynamic behavior for that particular system. So, we already have seen how it works, but just to recap, if I do dou ln Q by dou beta, what I essentially get is minus E bar. If I do dou ln Q by dou V, I essentially get beta P bar, and we clearly have F is equal to minus kBT ln Q. What is interesting is that not only this idea of partition function is useful to get the average value of quantities, in this case the energy and the pressure, but it is also important to get the fluctuations of those quantities from the average. And what do I mean by fluctuations is the following. So, when I said that the energy has an average value of E bar, all I mean is that my energy of different states will average to this particular value, but I do not mean that every state has the same energy. So, if you have, for example, so many states in the ensemble, they may happen to have energies higher than or lower than this particular E bar value. Only if I do an average over that, we should get the E bar value. But the point from the central limit theorem that tells me is that as I increase the number of systems, what we will notice is that this fluctuations in this E value will start to decrease. Now, let us see how exactly it works out and how the idea of partition function can give me the value of the fluctuations. So, let us say for example, you have some standard deviation of whatever distribution of energy you have. The other way to think about it is we can plot the probability of having an energy E j versus E j, and this is going to peak around some E bar value. So, we are interested in what is the width of this distribution or the standard deviation of this particular distribution. So, the standard deviation can be defined in the following way: the variance or the square of a standard deviation for the energy is essentially E minus E bar square, average of that. So, bar I am using to represent the average. So, I compute deviation for all the energy values with respect to the mean value, square it and then average it, right. So, clearly if I do not square, then you can have both positive deviations and negative deviations, and they may as well cancel out, and it does not represent the fluctuations from the average value. When we square it, both positive and negative deviations add up. So, it is a better measure of fluctuations in this particular quantity. So, I can write this thing by taking expanding this square term. You have E square plus E bar square minus 2 E bar average over this entire thing. So, average over the entire thing is the sum of average over each of these terms. So, I can write this as E square bar plus E bar square average minus 2 E bar average. Now, clearly for the first term we have to compute E squares and average it, and they will be different for every state. But in the second term it has already been averaged. So, you have E bar square. So, if I take an average of this again, I should get the same quantity again. So, this will be E bar square. Now, similarly here E bar is already averaged. So, we can write it as something like 2 E bar multiplied with the average of E, that is E bar. So, you have 2 E bar square appearing here. So, this is E square minus E bar square. So, now using the definition of the averages, we can write this as summation of E j square P j minus summation of E j P j whole square, where P j is the probability of having energy E j. So, this I can write as E j square e to the power minus beta E j by summation of e to the power minus beta E j minus E j e to the power minus beta E j by summation of e to the power minus beta E j whole squared. And now, let us see how we can get the same quantity if I simply take the second derivative of my q. So, let us say I start with my q as summation of minus beta Ej. We have already found this, but let us do it again. So, if I take the first derivative, what we get is e to the power minus beta Ej multiplied with minus Ej, and this can be written as q multiplied with minus Ej beta Ej exponential of minus beta Ej. So, q essentially is same as the denominator here, therefore, we have multiplied with q, and that is, if I move q to the other side, what we got was dou ln q by dou beta is minus E bar. Now, let us take a derivative of this quantity one more time and let us see what do we get. So, if I find dou 2q by dou beta square, that is taking a derivative of this guy right here or this guy here, that is equal to dou by dou beta of summation of e to the power minus beta Ej minus Ej, and that is summation over e to the power minus beta Ej minus Ej still appear there, but we have one more derivative of minus beta Ej with respect to beta, that is minus Ej, that is summation over Ej square e to the power minus beta Ej. So, if I start with this, if I put that in the expression right here, what we notice is that I can write my sigma E square as I had written earlier, so the first term now becomes the second derivative of q with respect to beta. So, dou 2q by dou beta square, and denominator is q, and the second term is the first derivative of q with respect to beta by q whole square, and this we can actually write as something like dou E bar by dou beta, because if I do that, then dou by, we can write E bar as dou ln q by dou beta with a minus sign, and that would have given me dou by dou beta of minus 1 by q dou q by dou beta, and that is minus 1 by q dou 2q by dou beta square plus 1 by q square dou q by dou beta whole square, and that essentially is same as minus of sigma E square. So, therefore, what we have been able to establish is that I can not only write E bar as a function of q, we can also represent the fluctuation in the energy sigma E also as a function of q. In other words, once I know E bar, I can also find sigma E square, but E bar I have found using q. So, I can find both the mean and the fluctuation using the idea of E bar. So, now I can write this particular quantity dou E bar by dou beta also as a function of temperature, that is using beta is equal to 1 by kBt, we can write dou E bar by dou beta as something like dou E bar by dou of temperature divided by dou beta by dou of temperature, and that is equal to dou E bar by dou T divided by dou T of 1 by kBt, and that will give me minus kB T square dou E bar by dou T. Now, what we can notice here is that the derivative of energy with respect to temperature has a physical meaning. It is the definition of my specific heat. In this case, we are working in canonical ensemble, so the volume is constant. So, this essentially is the specific heat at constant volume. So, not only the fluctuations are always present, but fluctuations also have a physical meaning. In this case, fluctuation refers to the specific heat. So, essentially my sigma E square goes like kB T square Cv, because sigma E square was actually equal to minus dou E bar by dou beta. Now, let us take an example of an ideal gas. So, for an ideal gas, the Cv is of the order of n multiplied with kB, and the energy is of the order of n multiplied with kBt. When I say order of, there can be some multiple there, that is not very important here. So, if I find my sigma E by E bar, that is, if I take a ratio of the standard deviation to the mean value, this will be going like square root of kBt square Cv by E bar, and that is roughly going like kBt square nkb by nkbt. Of course, the temperatures will cancel, the kb will cancel, and this tells me that the ratio of the standard deviation to the average goes like 1 over square root of n. So, what this means is, as n increases, as the number of molecule increases, your ratio of the standard deviation to the mean that characterizes the magnitude of fluctuation is actually decreasing, and actually if the n is very large, we may pretty much assume that the distribution is extremely narrow around the point E bar for large n pretty much going to infinity, and therefore, for n going to infinity, what we refer as thermodynamic limit we can pretty much say that the energy of system is roughly equal to E bar. So, keep in mind, although we are saying that the energy of a system is always equal to E bar or roughly equal to E bar because the fluctuations are less, that does not mean that I am discarding the effect of fluctuations, because fluctuations are really having a physical meaning here. The specific heat refers to the magnitude of fluctuations. So, if I say fluctuations are 0, that will mean that the specific heat is 0. That is not true here. All I mean to say when I say that my energy is close to E bar is that the deviation from the E bar of energy is very small as the n increases, right. So, the error that we make by this assumption of energy being equal to the average energy, that error will be small. That is not to say that the fluctuation itself are negligible. Fluctuations are always present and they have a strong physical significance. In fact, for systems for which n is not so large, then the fluctuations have magnified effect. simply as a result of the central limit theorem. Now, going further, just like what we did for the coin toss example, we can also write the distribution of energy as something like proportional to exponential of minus E bar square by 2 sigma E square, where sigma E square is given as kb T square Cv, and that itself means that the specific heat does affect the distribution, but the magnitude of that in comparison to the average energy decreases as the number of molecules increases in the particular system. So, this was all about the canonical ensemble. In the next lecture, we will take one step further and talk about what is known as a grand canonical ensemble. So, in the grand canonical ensemble, unlike the canonical ensemble, the number of molecules can also change. That would correspond to a case when the systems can exchange both mass and energy. And as you may expect, when I do a grand canonical ensemble, I will still have a partition function, but that partition function will not be the same as the canonical partition function. Nonetheless, using the idea of a partition function, we can still evaluate properties in the grand canonical ensemble. So, I hope to have convinced you that as we determine like what is the appropriate ensemble for the system to work in, the next step is always to determine the partition function, and once we have the partition function, we can go ahead and find all the properties. So, before I close in here, let us take one simple example and see how exactly it works out. So, it turns out for the case of an ideal gas, and I am not going to derive the expression, but the partition function is something like a function of temperature multiplied with volume to the power n when you have n molecules in the system. Now, it is not so difficult to see why it is true, because in the ideal gas case, we are assigning no volume to each of the molecules. So, they can pretty much be anywhere in the entire volume, and they can also sit on top of each other. So, there is no exclusion because we are assuming that particles are of 0 size. So, roughly speaking, the number of ways in which I can place one particle is going like volume V. So, number of ways we can place two particle is like V multiplied by V, V square. So, the number of ways we can place n particles must be V to the power n. That is the simplest equation of state that one can imagine. So, for this particular case, let us see how it works in right here. So, let us say if I am interested in the pressure. So, I know that dou ln Q by dou V is equal to beta P bar for the canonical ensemble, and beta we know is kBT. So, it is P bar by kBT. If I compute ln Q in this case, it is ln of f. By the way, this f has nothing to do with the previous f I discussed, some function, arbitrary function, plus n ln V, but this function is of temperature. So, if I do dou ln Q by dou V, for the partial derivative temperature is constant. So, the first term will not contribute, and second term will give me n by V. So, therefore, P bar by kBT is equal to n by V. That gives me the well known form P bar V is equal to n kBT. Keep in mind the n is the number of molecules here. If I work in terms of the moles of molecule, this is small n moles multiplied with Avogadro number kBT, and Avogadro number multiplied with the Boltzmann constant is my gas constant R. So, that gives me P bar V is equal to nRT. That is the form we are quite used to, right. So, once we know the partition function, we can find all the properties. The question, however, is how do we get the partition function, and that is something that is not very trivial thing to do, and clearly we have not discussed how to get the partition function so far. We know once we have partition function what to do with it, but how exactly we know for a substance what should be the partition function, that really becomes a slightly different topic, and we will do few examples in the later part of this course. So, with this I stop here. Thank you.